Hello everyone, nice to see you again. While we wait for the exact time to start, maybe just want to get your quick feedback about your current few weeks. Okay, I guess you may have a lot of tests and assignments and other things, okay, which deals within these few weeks, I guess, right? Okay, so do you have any tests or other things coming up, right? Because we will have our tests as well, okay, for this course, 2 tests, and we have to plan for that, right? So you just put in maybe the upcoming schedule for your tests and assignments and other things, okay, in the chat box. So at the end we will go through, we will discuss about that, right? So let's get started. Okay, so today we will go into the 2 chapters, right? 2 sections, right? So it will be the motor selections, the first one, okay, motor selections and flywheel, right? And as I have mentioned in the last sessions, we will try to cover everything, okay, and call this course to the end, right, for by today, right? Okay, so first we will talk about the electric motor, right? I guess most of you are familiar with electric motor, okay? You have seen electric motors in these modern days everywhere, right? From, maybe you don't see it, but you can actually feel it, okay, everywhere. First thing would be your handphone, right? So you have your handphone vibrating, right? So inside there is a vibrator, okay, which is controlled by electric motor, right? Then also you have your maybe laptop, your computer, where you can see there is a fan moving, right? So any movement like the fan pumps, okay, they come by a source of power, okay? And the source of power, in the modern days, the most common one is the electric motor, okay, powered by the electric, because we have the availability of the electric, okay, everywhere around the country, right? Most of the place, right? So you have your fan, your laptop cooling fan and everything, okay? So what is that, okay, the electric motor or machine? So it's just a machine that actually convert the electrical energy to mechanical power, okay? And the most common type that we have seen for an electric motor is the rotary type, okay, the type that is rotating, okay? So the life of an electric motors are determined by how well the motor is matched to the job and the service. So this is the most critical part, okay, because when we try to select a motor, we try to match it to the job, okay, or the task that it intends to do, okay? Otherwise it will jeopardize the motor. And also the service environment, whether it is dusty, there is a lot of moisture, the temperature, okay, so that it will not get damaged fast. The electric motor consists of 6 parts, okay, 6 major parts, okay. We have, this is the rotary type of motor, okay. There is a armature or rotors, commutators, brush, right, axle, the magnet, and also the final part, the power supply, okay. It can be a DC, the direct current you through the battery, like from our phone, or AC, okay, which is direct to the socket, okay, our home socket. In Malaysia we are using 220 to 230 watt, okay, at a frequency of 50 hertz, okay. So it depends mainly on the country. So the motors also will perform differently in different frequency, right? So this is the constructions inside. Okay, there is a casing, there is a magnet inside, the rotors, okay, the armatures, the commutators. Where for the DC motor there is a current connector over here, the commutator contact, okay, to give it a rotations, right? So the ideas of the motors, I believe you have gone through this before, right? So it's based on a law, right, where the electricity will be able to cause or induce an electrical magnetic field around a conductor when we pass through an electrics around it, right? So because of this conversions into magnetic, and there is a magnetic field, therefore we can use this magnetic field to actually detect or governs the movement of the electric motor, okay, to push it to move, okay, against another source of magnetic field, okay. So as we know, north attracts south, okay, and then north repels north, south repels south, right, and so on, okay. Then we also can see that this is the idea how it works, okay, under the Fleming left hand rules, okay, when we talk about conductors, okay, which is subjected to the electric field, okay, when it's come into a so-called magnetic field again, okay, around it, okay, therefore because of this magnetic field there is a force, okay, that's push the conductors to move in a certain directions according to, we call it as the Fleming left hand rules, okay. So whenever there is a magnetic field, the current of is flowing in these directions, it will cause the conductor to move, okay, or there is a force to go on that directions, okay. So physically this will tend to move away from this magnetic field, right, moving away, okay, until it disappears, right. So this is when we put it into the motor constructions, then it will cause it to move, okay, and then come down and continuously rotating, right. So there will be advantages and disadvantages, right. So for most of the electric motor, they are very so-called efficient, okay, they have the efficiencies more than 90% most of the time, okay, particularly when we select it at the proper we select it properly, okay, to match to the load so that it is operating at the most efficient conditions, right. Then there is also a maximum torque at 0 RPM, okay. So this would be desirable, okay, because it can stop, right. So you can make a motor to stop, okay, at a certain positions, okay, with 0 RPM, which you can do with a normal machines like engine, okay. You have to continuously rotate for an engine, okay. Then also it means that it is easy to control in this sense, okay. The power configurations can be done using software because it's electrical and electronically connected, okay. And if we reverse it for the DC motor, AC motor, it can become a generator as well, right. So this would this has been used in the regenerative motor, okay, attached to the hybrid cars wheel, okay, where whenever the cars move, okay, if you move, but then when we press the pedal to stop, okay, the rotations of the wheels is now converted back to the energy to be stored, okay. That is the idea behind the electric car and the hybrid car, where they try to save the energy, okay. Everything is running by the electrical power, right. It's also produce very less or almost zero harmful emissions, okay, except the magnetic field, right. Other than that, it doesn't produce film and other things unless you burn it, okay, means overheat, right? But then this one is more friendly to the user, okay, because it doesn't emit most of the gases, okay, dangerous gas, right? They also have less moving parts, okay, rotational movement, easy to construct, and we can precisely control and break it, okay. As we have mentioned, we can have it to stop, okay, with a certain torque, okay, so that it can hold at that positions, right? But then the disadvantages can be heavier, right? Only accept electrics, and we require the raw earth metals to construct a good magnet, right? Even the headphone, right? So even the headphone inside, to produce the sound, there is a so-called a kind of motor, okay, but then it's in a linear form, right, to attract and release, okay, so that it forms that kind of vibrations, okay, according to the frequency of the sound, right? So almost all electrical machines are made rotational, right? So in that sense, we would have the angular positions, angular velocity, and angular accelerations, okay, as the parameters to control, okay, for motions of an electric machines, okay. Then from that we can estimate the torque, right? This is where we can calculate the torque, and we know that the torque equals to R multiplied by the F, okay, the force. So this force, when the electric motor tells you there is a rated torque, meaning to say the motor is designed to produce this amount of torque, right? So that amount of torque, okay, when you apply it to your systems, this one, the torque would come from the motor itself, okay. Then this R is the radius, okay, to your perpendicular radius to your load, the force itself, okay. And this is where we design, okay, how far it is from our load, and the load would be the job that we intend to solve, okay, the force, okay, from maybe the gear or other things, okay. So this is the force that act, okay. So it should be, the motor should be able to cater for this, right? So from, if we know the rated torque, okay, therefore we can estimate what is the maximum force that it can carry, right? Similarly, we also have this torque equals to J alpha, okay, and from this, every motors and the system itself have a moment of inertia, which we will not cover how to identify that one, right? Once we know this, then we can also predict the behavior, how fast it can accelerate when we apply this amount of electric, and it produces this amount of torque, okay, how fast is accelerate, so that from there, most of the time the designer or the engineers will design such that it behave to the speed or acceleration that it wants, okay. It will accelerate fast, okay, and then it's slow, okay. So this accelerations is important parameters for them to control exactly. It's just like a printer maybe, so you have to accelerate, okay, from 0 to certain speed, it have to accelerate, and then what is the stable state, then it can start to control, so that you can print exactly at the positions that you want, right? You can estimate the work as well, okay. So the work equals to Fr, okay, and the power equals to Fv, right? So this is what we can estimate, okay, from these equations, okay, from our system, we estimate the kind of work, the power, the load that we want, and then from these parameters now we can start to select the suitable motor, okay, that we want, okay. And most of the motor nowadays, they still maintain so-called as a horsepower, okay. It's easier for everyone to capture, okay, horsepower, okay, because the industry has used this unit for a long time, and it's hard to them to convert, right, to the watt, right. So the conversions of 1 horsepower to the watt has been given in the previous lecture, right. So you can just briefly go through it, okay. So this is just a number that you have to maybe remember, right. Then the type of motor, as we have mentioned, there are AC, there are DC, and then for AC motor there are single phase, okay. This depends on the power supply, okay, at your home. So most of the time at home, okay, we are using a single phase, right. But then in larger factories, industry, okay, where they require higher load, then they will have a three-phase supply, okay, and these three-phase supplies will be used to move the bigger motor, right. Okay, so there is synchronous, asynchronous, there are also step motor, stepper motor, and so on, right. Now come to this, okay, so again, if we combine, or we try to we try to combine the previous equations, then we will notice that the power, okay, in the unit of horsepower, HP, okay, can be equals to the force, the radius, which we have get previously, and multiply by the speed, okay, to get the power. But then since they are in pound feet, okay, we divide by 5252 to get the horsepower, right. For the watt, if you want to use the power in terms of kilowatt, then you just have to do the same thing. The equations may remove this 5252, that's all, right. So the unit has to be SI unit, all right, to get the watt, okay. So now this is the common characteristics of a motor, okay. So most of the electrical motor, especially for those industry one, okay, they need this kind of data sheet, okay, this type of data sheets of the motor that allows them to see or to select properly, okay. But then for maybe for a sport device, they may not need this one, right, because the range of operation is very narrow. But then for an industry motor, then you can see that it can produce different kind of power, right. For a rated 75 horsepower rated motor, okay, it actually can produce different horsepower, okay. Why did this like this? If we intend to give it like maybe 30 horsepower, right, the efficiency actually drop, right. And then when the horsepower increase, then it will start to increase, then it will start to drop again. That's why we can see that when the manufacturer of the motor, they put a rated horsepower, usually that is the efficiency, the highest efficiency of the motor, okay. Where they try to rate the performance of the motor itself, right. So when we try to select such that our load is within, not too far away from the rated power of the motor, right. Then also there is a power factors, okay, as we see that for this motor, okay, the power factors also change, okay, from very low to very high, okay. And this power factors is related to constructions and how it converts the electricity to the magnetic field, okay. So therefore there is factors that it try to, there is a loss, okay, when we try to use it, okay, for this so-called performance or the load or the output power, okay. And then this is how we can adjust it, right, to the horsepower, right. We will not say that in order to reduce the power consumption, we reduce the current, okay. It would be it give us an idea of that if we give this amount of current, okay, then it's actually produce only 10 horsepower, okay. Therefore a motor, we still apply the same watt, maybe 220 watt, okay, for home, okay. But then the load itself, okay, may determine how much current it will draw from your socket, okay, from your electrical socket. So if you have a electrical fan, okay, electrical fan at home, okay, and it is operating, usually they will select at the rated horsepower, okay. Let's say it's rated at, now your home fan is operating at the 75 horsepower, the best one, all right. What if you remove the blade, okay? If when you remove the fan blade, okay, then the motor doesn't do much work, okay, because the fan actually rotating, and it has a kind of load. When you remove it and you turn on the electricity, means the load now drop, okay. It may drop to, let's say, 40. So you still connect to the same socket, but then it draw lesser current, okay. This is the idea of the motor itself. Usually we don't specify the amount of current that it intake, all right. But then this is an indicator whether the motor is working properly or not, okay. Usually there will be a very stable current input, okay, drawing from the socket, okay. If it drops, means there is a problem, okay. The load or the fan may be loose, okay. For example, if you have an industry fan, okay, which is not connected directly to the motor, but is through a belt, okay, because the fan blade is very big, okay. So you need a fan belt to connect it. So when this start to drop, okay, the current being drawn from the socket getting dropped, it means that the load getting lesser. What happened? How the load getting lesser is because probably if the fan blade remain the same, it means there is a slippage between the belt and the pulley, okay. When it slip, right, so meaning to say whatever you draw is it can rotate easier, okay, because you don't have the system itself doesn't now connect properly, okay. The load is lesser, okay, because of the slippage. So it tells you something is wrong, just like our body, okay. When we have flu, it tells us something is wrong, right, because our body or the system itself will operate at a certain range of current, okay. But then if the fan, okay, again the same example, if the current draw now increase, again there is a possibility that the system now, maybe the fan start to broke, okay, maybe lost, okay, broke. Why it broke and caused the load higher? Because of the increase of the load itself, okay, due to let's say it get a lot of dust, okay. So the fan is heavier to rotate, so the load is heavier, and also when the blade is not balanced, okay, then there is a centrifugal force, okay, that creates a kind of fluctuations, then the load also increase. And also there is a possibility that the belt is stuck, okay, in between the pulley, so that it requires more loads to operate, okay. So this is the way of interpreting, okay, why the current increase and decrease, okay. It is mainly based on the characteristics of the motor, right. Then also we can see that the speed and the output power decrease, okay, the motor torque and speed decrease, okay. So when you increase the speed, the torque actually decrease, okay, even for the motor, okay. So the motor itself, you can still control the speed, okay, by supplying different amount of ampere of power, right? So this is the idea of how you can select properly. All right, so that's why selections is important, and it should match to the load that we want, right? Then also the motor itself has overload protections, mostly for the industry one. Okay, so it tends to protect the motor control, and the motor branch circuit conductor. Okay, what they protect, they tend to protect against overheating. Okay, so when it is very hot, then these protections or this protector will start to slow it down, or maybe to stop it directly. Okay, meaning to say the motor may get fire. Okay, that's why before it happens or before it burns, this protector will start to cut it off. Okay, how it protects, they may not need a temperature sensor. Okay, they just need to detect the amount of current it draws. So when the current drawing from the power source is getting higher, means the heat is getting higher as well. Okay, so they will start to block it. Okay, just like our fuse. Okay, and this motor overload protections also is referred as a running protections. Okay, typically in two ways: the solid state overload relay, okay, or the thermal. Okay, this one, thermal overload relay, which it's not exactly detecting the temperature, but then the way of it relates to the temperature, right? So this is where you can see the motor data. Okay, especially the industry one, they have this plate. Okay, and this plate is very important to be there, so that whenever faulty with the motor, we can check what is the specifications of the motor previously, and then if the motor is faulty, you can, as an engineer, you can plan to select a new motor. Okay, if this motor no longer there, or maybe the motor is not suitable anymore. Okay, so from there you get an idea on what numbers to start with. Okay, because we assume that the selected motor in the systems are a good one. So if it's already there, then we can just use it for our design, right? To select the proper motor to replace the faulty one, right? Otherwise, if you are the engineer who designed this system without this, okay, therefore you have to select accordingly, according to your load, and then from that you put it there. Okay, and this will tells everyone that whenever this system's fault, okay, you have to replace the motor, okay, with the other motor that are equivalent in terms of performance, right? So these are the type or considerations that you may able to consider, right? The insulation class, okay, which would be the related to the environment, okay, whether it's moisty, heated, very hot environment. Okay, so this will tells you whether the motor is suitable or not, okay, with respect to the environment, right? You can see that this is the insulation class A, B, F, H, okay, for different parameters. Alright, so we have the ambient temperatures, okay, the temperature that we expect the motor to run, okay, and then the duty cycle, how long the motor can run at full load without overheating. So again, this is the characteristic of the motor. So if you intend to run the motor at full speed for very long hour, then you have to select this duty cycle or consider these parameters inside your selection as well. Okay, then also the power factors, the ratio of true power used in watt, right, when it delivers in terms of percentage, right? This is how you can see the the typical NEMA design class, okay, class A, B, C, D, F, all right, with the full load speed range, okay, and this is how you can characterize this, okay. Usually for a class A, the normal type of load we use class A, okay, general purpose. Class B, okay, this is the normal characteristics, okay, when they classify the electric motor, right? So high torque is class C, high torque resistance is class D, and so on. All right, so if you have questions, you just put into the chat box, so we will come back, okay, when we have the time, right? So now we will continue with the motor selections, okay. So when we do the motor selections, it's like a design, okay. Even though we don't design the motor now, okay, it is our task as an engineer to be able to select, okay. In most of the case in the industry, we don't design the motor, right, unless you are working in the manufacturers of the motor, just like the bearing, okay. You have to select instead of design, right, because these are the component that you need, okay, for your operations of your system itself. Therefore, in order to select properly, you have to ask ourselves, okay, what we actually want, okay, what we want. So what is the purpose, whether we want it to be used for different purpose like food processor, printer, and other things, okay. Then from there, you know the constraint, the environments, okay. By knowing the purpose, then you know if you are using it for a food processor, means you are using it, maybe if it is big one, then it should be in the factory. If it is a home one, then it should be suitable in the maybe your kitchen. All right, so you have an idea of the environment, all right, when we ask this kind of questions, okay. So once you know the environment, then it will give you an idea of what or which to select, okay. Then also what type of motor are suitable for our need, okay. You have to know again, if it is for home use, you never select a motor with a 3-phase, because home doesn't have 3-phase, okay, unless the home is really special, okay. You have to ask the SSB or anything, the contractor, to actually install a 3-phase line for you. Otherwise, you don't see any 3-phase, right? So the type of motors you are going to use, right? And also for a phone, okay, you can see that in this phone there's only a USB-C, right? Then from this you will know that the type of motor that you intend to select, it cannot be AC anymore, it should be DC, right? Then is the motor to load match when starting or running, right? What is the response time you need, okay? But then these questions would be more on the electrical side, okay, or those who have attended a course called control engineering, where they try to match the performance of the motor according to the response time, okay, how fast it react when we give a power to it, right? Then also under what conditions, is it underwater, hot, or dusty, right? The factors of selections can vary, okay, from, okay, then all this depends on speed, power rating, okay, the power that you intend to use, right, according to your load. Then duty cycle, load torque, operating environment, and other specific requirements, okay. Then the speed for a motor generally around 500 to 3000 RPM, normal typical speed for electrical motor, okay. Then the change speed and other things will be where you intend to reduce or increase the speed and the torque according to the load, right? So the motor come in with a rated torque, rated power, rated speed. Okay, so this, if based on this, you can start to select, okay, based according to your system. Okay, then also we have the power rating, okay, which is the highest power input allow for motor to continuously run, and then the duty cycle, as we have mentioned previously, the way we use it, okay, the percentage of one period of the electric motor, how long we want to supply the electricity, okay, within a certain period of time, right? So we call that as a duty cycle. And then this is the typical motor data sheet, okay, that tells you the ambient temperature, the thermal resistance, okay, the class, okay, and how it can mount, the protections, okay, and other things, right? So you can see that inside there is a plastic self-lubricating bearing as well, right? Then the technical part would be the rated frequency. So you can see at the rated frequency, the speed in Malaysia is 50 Hertz. Okay, so we only consider this part 50 Hertz, right? If you are in US 60 Hertz, then you consider this one, right? So the speed would be 500, power consumption will be 2.4, output will be 0.5, running torque will be 0.95, right? So you can see that this is the performance of the motor at the rated frequency, okay, and then rated voltage, okay, and this is the characteristics, okay, the duty cycle is 100% and so on, right? Now this is the load torque, okay, what we can consider, okay. So the load torque is related to your system, okay, where we call this as a load, okay, what force we want to carry. So let's say this is your motor that we intend to select, right? And since a gear, okay, to our winding machine, a winch, okay, for let's say an elevator, okay, a lift, okay. So inside the lift, then we will say this lift is for maybe 10 person, okay, so 10 person, we roughly estimate one person is 100 kg, so 10 person is one construction of the lift, maybe 200 kg, so 1.2 tons of load, okay. So you have to just calculate back, okay, to 1.2 ton convert to force, okay, 12,000 Newton, okay, and then the reductions of speed and so on, let's say reduced by 100 times, so it's become 120 Newton, okay, if it is, okay, so 120 Newton, so the load now become 120 Newton, okay. So this is how you can convert back or to get the load acting to your electric motor, right? So now your electric motor will have to consider two parts, okay. Either this is constant torque, okay, it doesn't move up down, it just continuously rotate, just like your electric fan at home, you just press it on and it's just constant torque, it doesn't change, okay. Then in that case you can select the proper conditions, okay, for your, okay, let's say constant torque, so it will be constant torque, right, throughout the movement of the thing. So whereas for other type of torque, then when we pump waters and other things, then it will start to change, right? So the torque requirement may be at first very high, then we stop, okay, and so on, right? So it change throughout the situations. Therefore, again, you can see that this is the load torque, okay. It may increase at time, and the motor torque characteristics running at 100% and 50% of the watt is different, right? So you can see that if you are using 100% watt, okay, to meet this load torque, okay, this is the point, okay, where it match. But then if we want to reduce the speed, this ns is the speed, okay, so we can lower down the wattage, okay, then the speed will reduce and it now match to the load over here, right? So this is the characteristic, let's say the characteristic of your systems, okay, assuming the torque increase when the speed increase, okay, let's say, okay, this is the fan pump type of characteristics, okay. The faster the fan rotates, then the load is increased, so therefore this is how you can shift, okay, to match the performance, right? Then also this is the operating environment, okay, as we have gone through previously, the ingress of materials, waters, okay. Then also some of the motor require cooling arrangement and cooling circuit power, right? So you can refer to this. The motor efficiencies now is about how much losses, okay, or how much power actually being output, okay, when they receive 10 watt, okay, whether the actual output is still 10 or not. Usually it's get reduced due to various losses, okay, like the losses in the core and the losses in the motor, okay, due to various factors. And this is how we can calculate the efficiency, okay, output power divided by the input power, okay, typical equations, and the output power can be equals to the input minus the total loss, and the total loss can be theoretically estimate, okay, using these equations, right? Now how to identify the efficiencies, same equations, okay. So if you have a small motor, output power measured by this mechanical brake, okay, so you have motor. How we can measure the performance of the motor? Usually we just use a gauge, okay, connect with the load and we put in the load over here, okay. So we call this as a mechanical brake, okay. So this is a typical way to test a motor, right? Then we will run it and see what is the reading over here, right? So in order to know the torque, okay, being supplied by the motor, it is given by the W minus S, okay, times the R, okay. R is the radius, this R, okay. So this is the W, this is the S, right? So you fix the weight, you read the S, okay, multiply by the R, you know what is the torque, okay, actually given by the motor, right? So based on that, you will know what is the actual output of the motor, okay. From there, divide by 60, okay, because we have the speed as well, is RPM, right? So we have to RPM per minute, so we have to divide by 60 to get in hours, to get in seconds, okay. So in order to get the watt, okay, in terms of watt, so from that output power divide by the input power, okay, direct from your current, okay, the current direct from your power source, the current multiplied by the watt, then you get the input power. Then from here you can estimate the efficiency of your motor, right? So again, this is another constructions of the brake type, okay. Instead of putting a load over here, you can put the two force measurements, okay. So the difference between these two give you this, okay, the difference between these two, right? So same calculations, right? This one is to identify the torque, okay, and the brake power, right? So far no questions yet. All right, so we will continue, okay, so that we can end it faster. All right, now we will talk about the flywheel. Okay, the first part will be the motor and the selections. Okay, how we characterize a motor according to the torque applied. Right, now we go into a flywheel. Okay, and this flywheel we don't intend to actually design, because this would be very mechanical, right? And okay, let's see. Okay, so what we intend to tell in this sections is what is flywheel. Okay, to understand what is flywheel and how it operates. Okay, and what are the considerations inside it. So the purpose of the flywheel is to act as an energy store. Okay, again, whether you realize it or not, this is everywhere. Okay, in a mechanical system, for example, in your engine. Okay, so you have this part, right, the bottom part. Okay, that part is what we call a flywheel, right? So this flywheel act as an energy store. Okay, so that when the conditions allows, if you rotate this mass or this flywheel faster, okay, and when there is no operations of the power source, then because of the momentum it will continue to move. Okay, so that it release back the energy, okay, when it from what it has received due to the power. Okay, therefore the flywheel can be used to reduce the power capacity of the power source. Okay, and then also to reduce the amplitude of the speed fluctuations. Okay, then you can see that the flywheels for a steam engine. Okay, you can see a flywheel for a steam engine and inside your engines. Okay, also it has been used in electric motor as well. Okay, when we are dealing with a load that are erratic and very high. Okay, for example, in a shearing machines. Okay, shearing machines means machines that used to cut blade or maybe metals. Okay, so you put in your metal sheet. Okay, and this shearing machine will just drop and cut. Okay, so to produce this high load to cut the metal. Okay, therefore you need to store the energy into a flywheel, and when the amount of energy is sufficient, okay, because you may just put a small motor and rotate, so that the flywheel now store the energy. When this cutting motions drop, okay, so this flywheel now, because of the high momentum, it will now move the blade down, okay, and cut it off. Okay, and when during the cutting, this flywheel will now subject to a sudden stop. Okay, but then it not stopping. Okay, it's still moving, but then the amount of energy now reduced, so you will again supply continuously, actually a motor continuously supply to the flywheel. So this flywheel will act as a energy store. Okay, so you can see that the power capacity now reduced. Okay, you don't have to actually give a exact high number of amount of energy to cut, but then you store it in the flywheel. Okay, the idea is just like you want to wash an object. Okay, let's say you want to wash it with 1,000 gallon of water. Okay, at maybe 2 seconds. Okay, 2 seconds you have to wash it using 1,000 gallon of water. Okay, so in order to do this, you need a water tank to store. So this flywheel is something similar to the water tank, so that the water will keep supplying until it gain 1,000 gallon of water, and you just open the valve. In 2 seconds, it's drained off all the water, but then the water still continuously supply to your water tank, right? So and then you close it, and then it restore back the amount of energy. Okay, so this is the idea of the flywheel, right? So in that sense, you don't need an exact pump that able to pump 1000 gallon per 2 seconds. Okay, that is very high. That's why this is the idea of the tank, similar to the flywheel, to store it before you use it. Okay, so it have a cycle. Okay, how long it takes before you can use it for the second time, right? And usually this kind of application is not a continuous type of applications. Okay, there is a cycle. Even in the engine itself, this is not, I would say, not a continuous operation, because you can see that the ignitions of the spark, okay, or the electric, okay, is periodic. Okay, you can have a periodic, so that you have to store it. Okay, or else you burn it. Okay, then it stop, right? We don't want this kind of situation. So usually this flywheel is to store, okay, to allows us to use it at the different erratic conditions, right? So the design procedure will be, we calculate the moment, the turning moment, okay, obtain it, then we calculate the moment of inertia of the flywheel. Okay, so this flywheel design is mainly depends on this moment of inertia. Okay, and there it goes. Okay, the torque of anything, okay, input and output, can be given by I alpha, the angular accelerations of this. Okay, so if you apply a torque on one side and this is your flywheel, the torque on the other side, so you can calculate the difference of this torque, okay, and the angular accelerations that you want, and this is the moment of inertia of your flywheel that you intend to design, right? So the idea is here, let's say this is the characteristics of the load, or yeah, the load, or that you get. Okay, you increase the moment and then decrease the moment, and so on. It's continuous, but then it's not, in the sense it's not flat, it's not continuous, but then it's going up and down, it fluctuates, okay, in terms of the turning moment, right? So from here we will find the average, okay, of this is one cycle. Okay, one cycle of our flywheel. This is 2 pi. You can see 2 pi is one revolutions of the flywheel. Okay, so the energy output will be calculated in this way, right? Okay, so this is where it comes, right? So we draw an average line, okay, and from there we will calculate what is the energy, okay, that it can store. Okay, so energy is basically the torque and the revolutions. Okay, so in the graph way we just get the area. So let's say this is 3.52, okay, for this area. So from the average, let's say this is E, so from the average at this point now, the total energy stored is now E plus 3.52, okay, it increased, but then after that it decreased again. Okay, so we decrease again to get this amount. Okay, average is E, alright, then increase again, you just plus this value with this again, you get this one. Okay, minus again, plus again, minus again, plus again. Okay, so eventually in one cycle this will return back to the original average power, right, or energy store. So therefore you can see that there is a maximum and there is a minimum, okay, energy throughout this cycle. There is a maximum energy stored throughout the cycle, and there is a minimum energy stored throughout the cycle. Okay, so from here we can calculate the energy, the change of energy, right? So the highest minus the lowest, so we get the changes of energy throughout this so-called period which we have identified. And then in order to design for the flywheel, this is the parameter that we intend to use to design, right? Others are the coefficient of fluctuation, which is depends on our desired parameters, and the operating speed. Okay, so this will be fixed, this will be fixed, and these two we can get, and this I is what we can design. Alright, so you have to design a moment of inertia large enough to store these changes, to supply enough energy for these changes from the highest to the smallest, right? So this I is depends on the constructions, okay, of the flywheel itself. Okay, so if the flywheel itself is a pure solid, then the moment of inertia can be estimated using this one. If it is a hollow type, maybe a rim type, okay, so a rim type, so the highest mass will be at the outside, okay, so just like this hollow, then the moment of inertia is given as such. Okay, so this is how you can design for a flywheel, right? Next, we will go into the last part, okay, assembly, access, and maintenance. Okay, this would be related to the machinery cost, okay, or why, come back to the questions like why we want to maintain machines or a system. Okay, so we will see that the total machinery cost can be reduced, okay, when the machinery size is usually greater, right? But then whether to replace the machines or the systems or to maintain it, okay, there is a few strategies. Okay, it depends on the machinery cost change over time. The machines will depreciate, okay, the repair cost and the performance that you have to consider. Okay, and when we decide on whether to replace or not, then also we have to consider the reasons, okay, why we want to replace the machines, whether it is cost minimizations, okay, just like previously AirAsia, they bought a lot of airplane, okay, and they changed their previous fleet of airplane, okay, to a more fuel efficient type of airplane. Okay, why? They have to do the calculations whether the saving of the fuel is justified to replace the existing one or not, right? So also the reliability, whether it's lesser maintenance or not, is it worth, okay, to change, right? Then also whether we have to match with a new technology or not, whether there is an increase in capacity or not. Maybe previously you need to pump 1,000 gallon per second of oil or liquid. Okay, now the capacity increased to 1.2 kilogallon per, so the capacity increase. Okay, and also the machinery market, sometimes the machinery, because getting more common, and or maybe a raw material is cheaper, then the machinery cost may decrease sometimes. All right, so it depends on all these factors whether you want to replace it or to continue to maintain, right? So generally to replace, there are several strategies. Okay, whether you want to replace regularly, okay, over a certain period of time you want to replace. Okay, maybe you want to use machines for 2 years, you replace, 2 years, you replace. So from there, because of this strategy, you will start to see that every 2 years you will you will replace it, then you will put lesser cost on the maintenance. You don't intend to maintain as good as you want to keep it for 10 years, right? So it will be lesser maintenance cost, okay? Fewer timeliness loss. Okay, timeliness loss refer to the loss of opportunities because of the time, right? Meaning to say the machine breakdown and so on, because you keep changing every 2 years, so the machines is every time is fresh, is new, right? But then the disadvantages will be expensive. So if you want to do this, either you do it like a leasing type, okay? You just lease it, like renting it, and then after 2 years you release, you don't want to rent it anymore, right? So this is a way of strategies, okay? Or another is rollover ownership plan, means after 2 years you will have your own client to supply to them, okay? This is rollover ownership plan, okay? Also, you can also replace something every year, okay? Instead of everything replaced every 2 years, you may select, okay, this year's our target is for replace certain amount of machines, okay, not everything, okay? So this is another strategy to avoid a large cash outlay, okay, every year due to replacement of everything, okay? But the disadvantages would be to replace the machine unnecessary. Sometimes you just replace something for the sake of you want to replace, okay? So that would be the disadvantages, okay? Another two strategies would be you may postpone the major machinery purchase until you have sufficient income, or another strategies will be to keep it forever, okay? So this is the least cost, but then you have the risk of breakdown, okay? And you are willing to use it, the old technology, for a very long time, forever, right? Let's say 20 years, okay? So you have to justify, okay, whether or not to use this kind of strategies, okay, whether it's critical or not, right? So this comes to the part where whether you want to maintain or not, right? So to assess the maintenance now, okay, we have several methods. So one of it is the Pareto's approach, okay? They call it ABC analysis, okay, based on this paper, okay? And what they do is they intend to analyze the downtime of the system or all machines, okay? And they group them into the A, B, and C part, right? So you can see the ABC analysis, whether the frequency faulty per component is frequent or not, okay? Frequent to rare, okay, in that component, and the significance of the downtime, total downtime, okay, whether it is seriously affect the whole system or the operations of your factories or industries or not, okay, from low to high, okay? So this is the ABC part, okay? And from this paper, they actually found that, or grouped them, and they found that most of the time this kind of system, like the tooling system, the machine control, the turret, the sensors, proximity switch, and the feeding device are very critical, because that is the most common part that fault, okay, commonly used, but when it fails, it cause a serious implications in terms of downtime, right? So this is the A. And the other part, like the conveyor, again very frequent, but then the impact may be lesser, okay? Coolant supply, okay? So you can see that even the fitting and the line, which not very rare to break down, but then when it breaks down, the the impact will be significant, right? So you can see that the overall of the breakdown impact, right? Then now when we come to the machine maintenance, there are generally three common practice. Okay, we call it as corrective, predictive, and preventive and predictive. Okay, so again from this paper, okay, it's similar. Preventive, this inspection is the predictive type. Okay, corrective, as well as the kind of improvement you try to improve instead of not only maintain but you improve the systems. All right, so this is several type of maintenance strategies. Okay, so what is the corrective maintenance? Corrective maintenance is the kind of maintenance that you will do when there is something wrong. Okay, means it's already start to break down. Okay, it's already break down. Okay, so we call that as corrective. The screen doesn't work anymore. Okay, you do a corrective maintenance. Okay, the roller or the bearing is not it's not moving anymore. We do that as corrective, and this corrective maintenance is usually urgent, right? You cannot wait, right? But then there is a preventive maintenance, which we will do it by time. Remember when we do a selections of bearings, okay, we calculate the lifetime of the bearing. Okay, so from there you will estimate how long it would last. Okay, and usually those manual will tells you for bearing you have to change every 5 years. Okay, for the engine oil you have to change every 3 months. Okay, so this kind is a preventive maintenance, because from the studies they know that the oil after 3 months running continuously, there will be amount of debris that will cause problem, okay, in the long run if you don't change it, and also the quality of the oil will change. Okay, so we call that as preventive. Even though before it breaks down, we change. Okay, we don't care whether it's still working or not, we change. Okay, according to time or maybe a certain amount of operations hour, or in car is the amount of distance travel, right? So that is the preventive type of maintenance. For the predictive type, we call it is the inspection type. Okay, so this type of predictive maintenance is more, how would say, technically it may require more technical knowledge, okay, to predict whether the part or component will come to faulty or not. Right, so this is a predictive maintenance. Okay, so how they usually do the predictive maintenance, the easiest one examples would be a car wheel. Okay, let's say a car wheel. So from a car wheel itself, whether we have to change our tire, the wheel or not, we can monitor, right? You just go to inspect whether the rubber thread is still there or not. Okay, you just inspect. It's still there is still maybe 2 millimeter depth of thread. Okay, is it good enough? Okay, how long we have to maintain it? Okay, so from there you can estimate. Okay, for example, starting is 5 millimeter depth, okay, or 1 centimeter depth of thread. Okay, but then after 3 months it become 2 millimeter depth. Okay, so from there you can estimate how long more it can last. Okay, that is the kind of predictive maintenance. And usually predictive maintenance, you want to assess the actual state of it. Okay, we would use this to replace or to maintain the component that are easily get access. Okay, for example, your wheel, easily for you to actually monitor the status. okay, all the I would say this component itself is it's difficult to reach. For example, let's say your boiler, okay, inside the boiler you have a lot of component, okay, then in order to do a maintenance inside, okay, we don't want to stop it, that's why we don't want to do correction, okay, we intend not want it to like break down, okay, in the middle of your normal operation day, okay, and also we don't want to do a preventive, okay, because it's difficult to open up and so on. So in that case we may also use a so-called predictive maintenance. It can be like to monitor the structures, okay, using vibrations or sound. So you can ask an expert to come in, okay, they will provide this service for you, like they will use ultrasonic to detect how thick is the metals, okay, without opening they can put from the outside and check, okay, the quality of the sound, and they match it, okay, to check the various part of your of the structures and so on, okay. So this is the type of preventive maintenance, okay. You want to predict, and then once you know this would last for maybe 2 more months, okay, then or maybe 6 more months, then from there you will see whether your factories or productions line now will have a major shutdown or not, okay. So in this usually in this shutdown, you want to replace everything, so that in that one day you replace whatever necessary, okay. So this predictive maintenance is useful, okay, for those expensive component that may be hard to reach or maybe easy to reach, okay, but then you want to predict, okay, before it fails, okay, and you want to replace or maintain it before it fails, right? There is equipment maintenance software. We call that the popular one. We call that as the TPM approach software. Okay, total productive maintenance software. Okay, that's provide an online informations on maintenance related. Okay, because as I say, there are lots of informations that you have to jot down, like maybe after you install a new components, okay, what is the maybe the length of it, okay, or the thickness of the thread of it, okay. So after sometimes 3 months, 5 months, you will tend to forget. So that's why this software is where you put in your parameters, okay, that you want to control. Let's say the depth of the thread, okay, you put in, okay, then after sometimes you put in again. So this software will keep a record, okay, on how long you have repaired it, okay. Maybe after 5 months you repair it, so they will keep track. 5 months later they will start to count again. 5 months, okay, they will start to highlight the amount of components that you may want to replace, okay, because of maybe corrective maintenance. Some part get faulty, you replace it, you key in the dates, time, and so on, okay. So from there, these systems will collect all this information. Imagine you have thousands of components to replace in a production line, right? So it's, even though you jot it down, it's impossible for you to go through them again, right? So this is where this software intend to do, right? To monitor and control all the maintenance activity of the machines, okay? And most of the time, this kind of software, since they have all the data, by a single click they can generate the analysis chart, okay, to visualize it, okay, regarding the MTBF, okay, the mean time between failure, the mean time taken to repair, right, and the condition-based maintenance and others trend, okay, so that you can estimate when or where you should do a maintenance, right? So this is the failure matrix. Okay, the MTBF, the mean time between failure is this one. Okay, from your uptime after you repair, okay, how long it takes before it fails again, the downtime. Okay, so this is your in between failure, right, time, and after you down, okay, so how long it takes for you to actually bring it up again, right? So from this you will see that the shorter of this is the total operation time, okay, and the number of failure, right, how many times it fails. Okay, so from there, because the in between failure times may varies, okay, so we just get an idea of how long usually, okay, it will start to fail again. Okay, so this needs a lot of data collections, okay, for your own machines. Okay, so to identify what is the mean time between failure. So the shorter the MTBF, okay, means more frequent downtime and more distractions. This is the idea, right? Then another metrics of failure is the MTTR, the mean time to repair. How long, okay, long repair time, okay, how long it takes to repair. All right, so it's like this is where you can again keep track, okay, how long you need to repair and when you want to repair. So this is where you start to use it as a platform to plan for your next maintenance job, okay, or factory shutdown, so that you will know how long it needs to get all these things done, right? This repair may include you want to look for the part, ask the supplier or manufacturer to send the part from you, maybe from UK, Europe, and now due to MCO, whatever, the time will change, right? So there is this downtime problem. All right, so we intend to repair and estimate how long it takes. Okay, maybe in order to repair a certain part, you may need to open the hole, even though it's a small components or bearing inside a machines, but you have to open up everything, okay, in order to replace it or to repair it. Therefore, that is the downtime or the repair time that you have to consider, right? So this will allows you to inform, okay, to inform you about the maintenance decisions, okay, when to repair or to replace the asset. Okay, the asset means the machine itself or a component within it, right? So all this will tells you if the value keep increasing, means the machine start to get all and more maintenance will require, then you have to consider the cost and other things. So again, it come back to the cost part. Okay, you have to identify whether it is worth now to change or not, right? So that's all for this whole courses. Okay, so we have covered from the design concept, and then we talk about how to get informations, generalize the design concept. Now we come to the component, the typical mechanical component that we will use everywhere. All right, and at this last stage is about the electric motor and the maintenance. All right, so I hope you enjoy this whole course. All right.